Here's a blast furnace. In order to turn it on, it activates when the door is closed, and when the door is open, it turns off the circuit. It takes some time for the circuit to start up. So initially it starts with all the lights on, and eventually it fades and starts blinking. The way the blast furnace works is I'm using a transistor as an Esaki diode or a tunnel diode. So I'm using a 2N2222 NPN transistor hooked up the opposite way that creates this effect. So basically what happens is if the collector is grounded and there's around a 12 volt on the emitter, then that actually allows current to pass through this transistor, which is actually the opposite of what's supposed to happen. Current is supposed to flow from the collector to the emitter. But once the emitter drops below this threshold of around 12 volts, then no more current is allowed to flow through. So by adding a capacitor, you can slowly charge this capacitor to this threshold. And once it meets the threshold, the current from the capacitor can be sucked out through this transistor and power an LED. When the capacitor discharges, it drops in voltage, no longer allowing the current to flow through this transistor. The capacitor is always charging, but at a very slow rate. And so when the capacitor reaches its threshold, it discharges and then slowly charges, discharges, slowly charges, and creates this cycle. You're limited on how much current can pass through, but it's a simple way to get some kind of clock. So here's the circuit I'm using, and everything's a little hard to follow since it's pretty packed. Here I have the two circuits, the blinking on the left and the inverter or NOT gate on the right. Both the circuits share this 12 volt input and this ground here that gets connected through a jumper. Here in the middle is a voltage divider in order to power this LED that's not hooked up yet. When hooking up power, it does take a while for the capacitor to charge up and start the flashing circuit. Before hooking up the signal to the NOT gate, I'm going to power up this LED. So from the middle pin of the potentiometer, I will put to the LED. Something to note is that I have a resistor here before this potentiometer, and that's in order to protect the LED from gaining too much current. So you can see I'm able to max out the potentiometer and not burn out the LED. In order to connect both circuits, I'm going to connect the collector of this transistor on the left and connect it to the base of the transistor on the right. Now both LEDs are turned off, and so now I can move this potentiometer to a point where both will flash on and off. And there we have both circuits flashing. What's happening is that when there's no signal for this transistor on the right, then there's going to be around 3 volts for this LED to be powered. And that's because there's only one path for the current to flow through this LED. Now by adding a signal to the transistor, this opens up a second path for this current to flow through. And so these two paths have a combined resistance lower than the LED resistance. And so it greatly drops this divided voltage to where it can't power this LED anymore. Now when the left circuit discharges, that causes a drop and closes this transistor and increases the resistance since there's only one path for the current to run through. The higher resistance of the one path increases this divided voltage and allows it to power the LED. And so this is the basic idea. For the actual circuit, I added another capacitor in order to smooth out this transition of the blinking light, and so it slowly fades off. Along with the capacitor, I added a variable resistor or rheostat in order to finally tune the slow discharge. And so it can rapidly discharge or slowly discharge depending on where the rheostat is set up. Also, I have these two LEDs that are hooked up in parallel to each other. And so you are actually able to add as many LEDs as you want in parallel, but it will drop the brightness. This is where this potentiometer comes in handy because you can always just adjust it. I have all these potentiometers in order to fine tune everything since it can be pretty sensitive. If I turn here, you can see that now it's only affecting the middle. Over here I can change how fast the capacitor charges, and so by reducing the resistance, it can charge a lot quicker or a lot slower. Now, a disadvantage of using transistors this way is that it does need a higher voltage of 12 volts. And so if you want to implement it in a lower voltage circuit, then you will need a boost converter in order to supply that higher voltage. And so here I have the boost converter hooked up to the battery pack, which is around 3.6 volts, and it gets changed to around 12 volts for the circuit. In order to turn everything on, I have the battery pack hooked up to this little switch that's created with a copper foil tape. And so if the door is open, it disconnects the positive power going to the boost converter. I have it hooked up this way because the boost converter allows current to pass through even though it's not powering anything. So by having it disconnect over here, that means that no current is able to flow through the boost converter. And so on the door, I have copper foil tape that allows those contacts to be connected. So that's pretty much it. If you have any questions, as always, please let me know. And thank you for watching.